Hello everyone, my name is Lucas and I'm here to present slow feature preprocessing in deep neural networks for wearable sensor-based locomotion recognition. The slowness principle has its origins in neuroscience and potentially is a method performed within the visual cortex to reconstruct external causes of visual stimuli. It is applied to represent the external causes based on raw sensory input. One common example would be observing an animal in the wild, which might be moving around and performing various different tasks. By doing so, it produces a huge and intensive spectrum of visual stimuli. And yet, we are fairly easily able to keep track of the animal as one persistent object, which changes its location or activity much slower and smoother compared to the actually observed sensory input. The slow features are estimated by finding and extracting the slowly varying output signals which underlie a quickly varying input signal. The motivation behind our work is the fact that the computed slow features are capable of representing a broader functional spectrum than convolutional layers, including convolutions themselves. This led us into investigating whether these features could be used as a replacement or an addition to convolutional layers in a sensor-based locomotion classification task. The method used to obtain these features is called slow feature analysis, or short SFA. It has been applied to video recordings for detecting cuboids, shapes, and facial behavior. And SFA has also been applied to sensor signals from a Wii controller, which was used for gesture recognition. In this case, the prediction was performed with a random forest predictor. None of these applications utilized deep neural networks. In algorithmic form, SFA estimates transformation functions, which are used to extract output signals from a given input signal. The target is to minimize the slope of the output signals, which is estimated as the time average of their squared derivatives. The optimization is performed under the following constraints. The first one is zero mean, and the second one is unit variance in the output signal. These two constraints normalize the output, and they also avoid the trivial solution, which would be a simple constant. The last constraint demands decorrelation of the output signals and ensures the order, meaning the first output signal will always be the slowest. Decorrelation guarantees that output signals don't carry redundant information. The first step is to use a sliding window to slice the signal, comparable to a kernel in a convolutional network layer. Then there's the degree of the polynomial expansion applied. This allows for nonlinear solutions and thus goes beyond the potential of traditional linear convolution filters. In this example, the sliding window takes two samples and quadratic expansion is applied, leading to the transformation function g defined by these 5 weights. When we apply SFA with these parameters to our test signal here, we get the following weight vector, which is able to transform the signal into one which distinguishes the 3 present modes. For this study, we utilize the SHL Dataset, which is a publicly available dataset for locomotion and transport mode recognition. It was recorded with 4 smartphones, one on the torso, in the backpack, in the hand, and in the hip pocket. And with those, 8 different activities were recorded, which are shown in the diagram on the left. In total, 20 sensor modalities were captured, all sampled at 100 Hz. For this project, we're only going to use the recordings from the phone in the hip pocket, and also only the signals from the 3 acceleration sensors. These acceleration channels are converted into the magnitude of acceleration in order to negate the impact of the phone's rotation in the pocket. The resulting one-dimensional signal is sliced into 5-second long segments using a non-overlapping sliding window with the length of 500 samples. This is not the same as the sliding window in SFA. It just allows us to shuffle the order of samples and keep class balance in training, test, and validation data. We use the training data to learn the weight vector for the transformation function, and then we extract the slowest feature of each window. Such a feature will then be one data sample in the classification task. As baseline, we skip this and just use the magnitude signal window as data sample. For the actual classification, we use a deep convolutional long short-term memory network, which is widely used for activity recognition and a common benchmark for experiments. It consists of an input layer, which receives the sensor signals, or in this case the slow features, and feeds them through 4 convolutional layers and then 2 fully connected layers before predicting a class using a softmax layer. For this experiment, we changed the number of convolutional layers in the DeepConvLSTM by removing up to 3 of them to investigate the potential of SFA to replace them. All these 4 network constellations were tested with the baseline, which is just the raw magnitude signal, and on the slowest feature extracted based on the 2 SFA parameters, degree of polynomial expansion and window size. Cubic expansion is possible, but computationally not feasible, so only linear and quadratic expansion were included. For the window size, we tried different lengths between 3 and 100 samples. These are the results for linear expansion. Each row represents a different network architecture based on the number of convolutional layers. The columns show the number of samples captured by the SFA sliding window, whereas none refers to the baseline signal. The performance is measured as weighted F1 score, and the best result per architecture is highlighted. As we can see, there is a big jump in performance going from 1 to 2 layers, which goes from 70 up to 80% F1 score, and then there is a less improvement when increased to 3 layers, and none or even a negative impact when the 4th convolutional layer is added. That indicates that 3 layers might be the best setting for this dataset and task. SFA seems to be able to slightly improve the results, especially in the standard 4-layer network, where each SFA configuration reliably improved the results compared to the baseline. The same trends can be observed in the quadratic expansion scenario. Here the highest achieved performance is also 83.9%. This time this occurs in the 4-layer network though. Overall, again, there are slight improvements over the baseline, but no particular parameter setting is standing out. The results have shown that SFA is able to improve the classification performance when used as preprocessing technique for a deep convolutional network. In this task, a performance improvement of up to 2.2% F1 score was achieved. The results have shown that the difference between linear and quadratic expansion for this task is marginal, and surprisingly, even major changes in the SFA window size had only a minor impact on the performance. Future studies could investigate whether it would be beneficial to add additional training samples to estimate the transformation functions, since we only were able to use 100 windows per class due to time constraints. Furthermore, all the data in this experiment stems from the same user, so it would be interesting to train on a broader dataset or use cross-user validation. And with that, I want to thank you all for your attention.